Hi, this is Miss Fitzmaurice. So what I need you guys to do is I need you to go to page 5 of your Unit 3 packet. Okay, these are problems on friction. I need you to try 1 and 2. Give each one about 7 minutes. Okay, and then I'm going to go over the solutions, but try them by yourself first, or if you get really stuck, try the first one, wait for the answer, and then try the second one. Okay, so now that you've tried these, number 1 says a large crate of unfinished grating sits on the ground. Okay, this is me being sad about my unfinished grating. Okay, the coefficient of friction between the crate and the ground are mu k is 0.5 and mu s is 0.7. If Miss Fitzmaurice applies an 80 Newton force to the crate in the horizontal direction, A, will the crate move? And B, if it does, what is its acceleration? Okay, so first I'm going to draw my force buddy diagram. Okay, I know gravity is acting down on the crate. There's a normal force pointing up. Okay, I'm pushing. We can go F, H, F for my name. Okay, and there's friction going the opposite way. So, to figure out A, okay, it will just barely move if the force I'm applying, HF, is equal to the static friction force. Okay, so that's in the x direction. Okay, another way to write that is sigma fx equals max. Okay, it's FHF, my force, minus FF equals 0, and I need to know if this thing is bigger than this thing. Okay, in the y direction, and you might be saying, why do I care about x? Why do I care about y? I care about y because I don't know what Fn is. Because F, the force of friction, is really mu s times Fn. Okay, so I have to find out what Fn is. So sigma Fy equals may. This thing is not moving in the up-down direction, so Fn minus mg is equal to 0. Fn is equal to mg. In this case, Fn is equal to m, which is 10, times g, which is 10, and Fn is equal to 100. I'm going to take this and I'm going to plug it into my equation. And the maximum static friction force will be 100 times mu s, which is 0.7. Okay, so that's how much force I would need to push this thing to get it to start moving. Okay, this is equal to 70. I'm pushing with 80. So, yes, it will move. Okay, in B, it asks what's the acceleration. Okay, and this whole part is iffy. This was like, if this thing is not moving, this would be true. But it is moving because I'm pushing with 80, and the most that static friction can give me is 70. So my x direction, because it's moving, sigma fx equals max, is FHF minus FF equals max. I know that m is 10, and I want to know ax. Because this thing is moving, instead of using static friction, I'm going to use kinetic friction, mu k times Fn. So I have my force, which is 80, minus mu k Fn equals 10 ax. I can bring this 80 to, or I don't want to bring the 80 to the other side, sorry. I know that Fn is 100. That doesn't change. My up and down doesn't change. And I know that mu k is 0.5, so I have 0.5 times 100 equals 10 ax. Okay, 80 minus 0.5 times 100 is really 30 equals 10 ax, and ax is equal to 3 meters per second squared. Okay, so number 2, it's kind of along the same lines. There's a 30 kilogram desk and it's pushed across the floor. Okay, if the coefficient of static friction is 0.7 and the kinetic friction is 0.4, how hard will the student have to push to make the desk move? Okay, again, this is the same force body diagram. We have Fn is up, Fg is down. Now it's the force that the student is pushing with and friction in the opposite direction. Okay, so to make the desk move, we know that there's no acceleration, and to just barely move, Ff is mu s, our static friction, times Fn. Okay, so we have sigma Fx equals 0. To just barely make the desk move, we need Fs minus Ff equals 0. The force of the student equals Ff. We know that Ff is mu s times Fn. So I have the force of my student is equal to mu s times Fn. And now I realize I need to find Fn. Okay, same idea as before. We can write out Fy equals may. This thing is not moving up and down, so ay is 0. I have Fn minus Fg is equal to 0. I know that Fg is mg, and that m is 30, so Fn minus 30 times 10 equals 0, and I can solve for Fn. Fn equals 300 newtons. Okay, now I can go back to my x direction. I know that mu s, the static friction, is 0.7, so we have 0.7 times 300, and I end up with 210 newtons for Fs. Okay. For B, I want to know how hard the student will have to push to make this desk move at a constant velocity. If it's moving at a constant velocity, I know I need to use kinetic friction. Okay, so I have sigma Fx equals max. At a constant velocity, ax is 0. Okay, but instead of using mu s Fn, I'm going to use mu k, because moving means kinetic friction. Okay, so I have Fs minus Fs equals 0. Okay, I can use the same normal force as I did before. Again, I'm going to fill in my force, mu k Fn, but I know my normal force is 300. My kinetic friction is 0.4, and I can solve for Fs. the force the student has to apply is 120 newtons. Okay, this makes sense. So it takes 210 newtons to get it to start moving. Okay, that's when you use static friction. That's when you use this thing, when something is just barely starting moving. And then it takes less force to keep it moving, and when something is moving already at a constant velocity or accelerating, you use mu k Fn, and it takes less force. You've all experienced this when you push heavy things. It takes more to get it started than to keep it moving. Alright, so I realize these problems are a little bit challenging at first, but hopefully this has helped. And tomorrow we'll be continuing our tension SDLs, but you'll also be starting a new one, hopefully, in which you test out the coefficients of friction of your shoe.